Welcome to The Explainer. Today, we're diving deep, really deep, into the stuff that powers literally everything in our digital lives. We're talking about the fundamental physics behind the semiconductor.
Okay, let's just start with the device you're watching this on right now. You know, the one in your hand, or maybe it's sitting on your desk. At the very heart of that device, the brain that makes it all work, it's all built from this one really special kind of material.
And here's the wild part. This stuff has this kind of strange dual personality. On one hand, it can be a perfect wall, completely blocking electricity from getting through. But then, and this is the amazing part, with just a tiny little push, a little nudge, it flips. Instantly, it becomes a perfect highway for electricity, letting it flow flawlessly.
So how in the world is that kind of control even possible? And maybe more importantly, why is that one simple ability to switch on and off the absolute key to, well, everything? Let's get into it. All right, here's the plan. We're going to look at how we control the current in the first place, then dig into the crystal's energy levels. After that, we'll see how we can actually design these materials using impurities, get those charges moving, and then see what happens when electrons finally meet their counterparts, holes. And of course, we'll tie it all together to see how this becomes the engine of modern tech.
Okay, first things first. To really get a handle on this control, we have to ask a basic question. Why do some things conduct electricity and others don't? Well, it all comes down to what's happening on the inside, their structure. It all begins with this beautiful, perfectly ordered structure, a crystal. Just imagine a perfect 3D grid, like a jungle gym that goes on forever. That's the lattice. Now, at every single intersection of that jungle gym, you place an identical group of atoms. That's the basis. Put them together, the lattice and the bases, and bam, you've got a crystal.
Okay, so inside this perfect crystal, electrons are kind of picky. They can't just have any old energy level they want. They're stuck in specific energy bands. Think of it like floors in a building. There's a low energy floor, the valence band, where all the electrons are just hanging out, stuck in their apartments. Then there's a high energy floor, the conduction band, where they can roam the halls freely. And in between, a forbidden energy gap, basically no staircase. And the size of that gap, that's everything. In a conductor, like copper, the floors actually overlap, so electrons can just wander between them, no problem. In an insulator, like a diamond, the gap is massive. It's like the floors are miles apart. The electrons are totally stuck. But a semiconductor, that's the sweet spot. The gap is small enough that if we give an electron just a little bit of a push, a little energy, it can make the jump. And that is where we get our control. All right, so let's zoom in a bit. Where do these energy bands even come from? How do they form on the atomic level? Well, if you take just one single atom all by itself, its electrons have these very distinct, separate energy levels. But when you pack millions and millions of these atoms together into a crystal, all those individual levels start to interact with each other. They split, they spread out, and they eventually merge into these continuous bands of allowed energy. It's a bit complex, but that's the gist, and it's something that models like the Koronic penny model help physicists map out. But there's a catch. A perfectly pure semiconductor, it's kind of useless on its own. If you cool it down to absolute zero, we're talking minus 273 degrees Celsius, it's a perfect insulator. None of the electrons have enough energy to make that jump across the gap. So what do? We cheat. We have to find a way to hack the crystal to make it conductive whenever we want. And this, right here, is where the real magic happens. This is how we turn what is basically a rock into the foundation of our entire digital world. The hack is a process called doping. And yeah, it's pretty much what it sounds like. We intentionally sneak in a tiny, very controlled amount of impurity atoms into that otherwise perfect crystal. And this one tiny change has an absolutely massive effect on how it behaves. And we can do this in two main flavors. First, you can add impurities that have an extra electron hanging around. These are donor atoms because they're happy to donate that electron, which creates what we call N-type or negative material. The other way is to add impurities that are missing an electron. They're called acceptor atoms because they create an empty spot, a hole, that's ready to accept an electron. And that gives us P-type or positive material. So what exactly is a hole? The best way to think about it is like an empty parking space in a totally full lot. Because that one spot is empty, all the other cars, the electrons, can now shuffle around. One car moves into the empty spot, leaving a new empty spot behind it. So even though it's the cars, the electrons, that are actually moving, It looks like the empty spot is the one that's traveling through the lot. And since it's the absence of a negative electron, it behaves just like a positive charge. All right, so now we have our charge carriers ready to go. We've got free electrons in our N-type stuff and these mobile holes in our P-type stuff. So how do we get them moving? How do we create a current? Well, there are two main ways to make that happen. The first one is called drift current, and it's the one you'd probably guess. You apply an electric field, a voltage, and it just pushes the charges along. Super simple. Think of it like tilting a pipe to make water flow downhill. The second way is called diffusion current. This one's a little different. It happens all by itself when you have a bunch of charges crowded together in one spot. They just naturally want to spread out, to move from high concentration to low concentration. It's just like watching a drop of ink spread out in a glass of water. Okay, so what happens when one of those free-roaming electrons finally bumps into one of these mobile holes? This is it. This is the moment where all this physics connects directly to the technology in our lives, from the screen you're looking at to the lasers that read your data. This little meeting is called recombination, and it can go down in two very different ways. In certain materials, say gallium arsenide, when that electron drops into the hole, it has to get rid of its extra energy, and it does that by spitting out a little particle of light, a photon. That's radiative recombination, and it is literally how every LED and laser works. But in other materials, like our good friend silicone, that extra energy just gets released as heat. That's non-radiative recombination. And this, let's be honest, less useful, heat-producing version, it's usually caused by imperfections, little defects in the crystal structure, or something called Auger recombination, or even just the messy edge of the material. These all create little traps where electrons and holes can recombine and just waste their energy as heat instead of making light. It's a real efficiency killer. So you see, understanding and controlling all these little dances, the drift, the diffusion, the recombination, that's the whole ballgame. Because once you can master those behaviors, you can build the absolute cornerstones of all modern technology. If we design a material that loves that light-emitting recombination, we get LEDs and lasers. If we run that same process backwards, using light to knock electrons out and create pairs, we get solar cells and light detectors. But the big one, the most important one, is that by using electric fields to perfectly control the drift and diffusion of all these electrons and holes, we can build the transistor, the perfect, tiny, controllable gate, the ultimate on-off switch, and that is the fundamental building block of every single computer chip. I mean, when you really stop and think about it, it is absolutely incredible. We've taken a simple element, silicon, which is basically just sand, and by learning to hack its atomic properties, we have built our entire digital age. It really makes you wonder, right? What's next? What kind of world will we build when we start designing the fundamental properties of entirely new materials from the ground up?